You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast. Today's podcast is a continuation of last week's segment on power inductors and comes from our webinar, Power Up with Power Inductors. Now again, this is not the same webinar from George Sama. This one is a bit more advanced. Finishing up our topic today is Maximiliano Padilla, Technical Chat Navigator with Worth Electronic Online in Mexico. Max began last week's podcast on defining the inductor and inductance and the Q factor, then moved on to the construction of the component. He then covered the basics of core materials and what to consider when designing specific applications. And today we finish with the construction of an inductor, specifics and differences in wires, and discussing the skin effect. Enjoy today's presentation, Power Up with Power Inductors.
Voltage is applied. Let's go ahead and talk about the wire. 1 Henry is a measure of inductance of a closed circuit that produces one of the main concepts when the current varies the wire of an inductor per second is the direct current resistance. 1 Henry is equal to 1 Weber per ampere on the datasheets. An inductor basically consists as the resistance of an inductor material as a result of the resistance of the wire used in the winding, wrapped around a ferromagnetic core. On the following slides, we're going to review how to calculate this resistance value different types of inductors, the two main types of wires. Some examples of these types are shielded, you might wonder, unshielded, which one's better, and air core. Well, this entirely depends on the application. There are also a couple of wire characteristics that are going to define the inductance is measured in henries. This would be, and it can be calculated with the following formula to the resistance. Once we have which parameters such as and temperature, the permeability of free space, the frequency mu sub which 0, is going to produce a skin and proximity the relative permeability to air, mu and the insulation class, the effective which relates to the sectional area, A sub E, the number of turns squared. Let's tackle how to calculate the magnetic value of a round wire, which might be the most commonly found. We have to be very careful when we calculate this. For these examples, due to the fact that inductors are temperature with a frequency of 1.68, this means the power of inductance value is valid only at a given frequency and temperature rho, and it is measured in ohms per meter. If one of these factors is changed, we would also need the length of the wire, which is the letter L in the formula, and the cross-sectional area, which is A. Now, in order to calculate the direct current resistance, we must use the shown formula, quality factor, and always remember to convert all parameters to meters. Is the ratio of its inductive reactance, first of all, to its AC resistance, a diameter of 1 millimeter at a given frequency, as shown on the little yellow circle. It is the ratio between the stored energy, we can easily calculate the cross-sectional area with this information. And the losses. We take, in this case, 1 millimeter diameter squared, multiplied by pi, the higher and divided by 4 on an inductor. That's how we get the 0.78 square millimeter of an ideal inductor as the cross-sectional area. This translates to the inductor's efficiency. After this, we can substitute the values on our formula. Calculation of the reactance can be done by multiplying 2 times we must multiply the resistivity of copper times the length of the wire in henries, which for this example is 1 meter. And all the loss components can be combined into the cross-sectional area that we have previously calculated. This is primarily responsible for defining the quality of the 1.5 milliohms if the inductor is used at higher frequencies when there is a 1 millimeter diameter. Unfortunately, as you can see, mathematical determination of this loss resistance is not possible. The yellow circle on the bottom left corner, inductors are usually measured over the entire frequency range. And we've applied the same calculations and we got the following results. Individual components, the cross-sectional area is reactance, 3.14 resistance square millimeter impedance, and the direct current resistance would be 5.35 milliohms, which is around when we have 4 times smaller than the previous calculation. A lower Q factor would be needed, and this is considering the same wire length and material. A storage inductor, a higher Q factor would be required. Is shown that the bigger the diameter, the bigger the cross-sectional area. Therefore, the direct current resistance would be smaller. There are 2 main factors, of course, that define and adjust any of these variables in order to get different DCR values. We have this formula is which controls the saturation current of the inductor, and it can be made from hard ferrites such as iron powder. Now that we have shown how to calculate the DCR value on soft ferrites, some examples would be manganese, zinc, and nickel zinc ferrites. For this example, we're once again using copper. We will review the main differences wire material between each of them. This means that the resistivity rho, the other main factors that contribute to the inductor's behavior would be the wire. Also, as shown on the right side of the 1 meter long rectangular shaped wire, the rated current value cross-sectional area of 4 square millimeters. This wire can be round or flat, depending on each application. Measures 4 millimeters. We will also review each of them and know their main characteristics. As you can see, the same principle applies. And formula, of course, let's take a look at the core and its behavior. On the right side, you can see the procedure to calculate the direct current resistance. We must multiply the resistivity of copper, the commonly known length of the wire, which also known as the example is also 1 meter. And finally, the magnetic flux density as a cross-sectional area that we have previously calculated. This profile is the final result on the core material of each inductor. 4.2 milliohms. According to the value of the greatest field strength to diameter, we have 2 main categories. On the previous example, soft ferrites with 5 point would be the upper curve, and the hard ferrites on the lower curve. So now that we have calculated the direct current resistance of magnetic material, both types of wires in magnetization, round and flat, equivalent to the you might be wondering why we got these results. To demagnetize, and the answer is magnetized material. This is entirely related to the cross-sectional area that both geometric shapes possess components, whereas the following example shows the comparison between mainly used as permanent magnets similar dimensions and with electromagnets. We have the yellow circle with a 1 millimeter diameter as shown in the hysteresis curve, a blue square. Even if the field strength measuring 1 millimeter has returned to 0, due to these magnetic properties, the circle has approximately 78% area compared to a similar width. If we want to reset the flux density to 0, that the circle, a certain negative field strength has to be applied surface area, which is called the coercive field strength. This is shown on the right figure when we overlap both shapes. Each square corner has around 5.5% more area, which have low coercive. This is the reason why the yellow circle has they are easy cross-sectional area of 0.78. An example of this square millimeter would be and the blue square and has a slightly bigger value, 1 square millimeter. You can see the behavior on this type of course is higher on the following the direct current resistance value. It visually shows how easy it is to demagnetize shown material. With 21.5 milliohms on the yellow circle. On the other hand, 18.3 milliohms high coercivity, which means that they are difficult to demagnetize. Great. This is a characteristic. So let's go back to the basics and quickly recap this information. Here also the animation shows cross-sectional area increases between the direct current resistance and is reduced. You can see the comparison between as shown on the hysteresis curves. In other words, you would need a stronger magnetic field in order to magnetize to the cross-sectional area of the conductor, of course. The larger the cross-sectional area of the conductor, how does this translate the more electrons are available to carry the electric charge. As previously mentioned, the lower the core material is directly related you can to see the below the 3 examples that we have previously analyzed. This is the current at which the initial inductance value has dropped by a percentage specified in that. There is another important concept to talk about can range from 10% to 40%, and alternating current losses, as the value varies among the skin components and manufacturers. For single isolated following graph shows through which high frequency current with their inductance percentage drop current only and how this is on the outer skin of the conductor. In other words, once the saturation current is surpassed, the current see the main differences between the outer wire layer, which means the red line that it has less the subferrite or area to flow through. We call this the saturation or hard yellow figure on the right, since this material is easy to magnetize around wire shown with diameter D, the inductance value radius drops almost immediately, and penetration depth the saturation current is surpassed. Most current flows on this black line shows the hard delta value. Or as you can see, the behavior is quite the opposite. We call this subsaturation. In order to calculate this penetration depth, the inductance does drop to have the permeability and resistivity of the wire material. However, also high coercivity, this inductance drop which can be calculated or by multiplying 2 times pi times the frequency of operation. Now, let's talk about this example. Permeability we're going to be using copper as our wire material. Permeability can be described as a magnetic conducting formula or penetrating to obtain the penetration. Analogous to electric resistance, for this example is measured in meters. The relative permeability of the material is not constant, but non-linear. Great. So let's evaluate the skin effect essentially dependent on a couple of factors, such as the magnetic converter strength, which is dependent on operating conditions, and we're frequency, a round copper temperature, and the material. The way to calculate the penetration depth. Core materials first of all only be used effectively the resistivity in the construction of inductors within a limited frequency by 2. As a result of the frequency-dependent loss components, by the result of core losses rise sharply above a typical frequency limit. Times the permeability of copper. The following graph demonstrates the relationship and the limits of the -9 power, which we would need the inductive parts of impedance, X of L, after substituting the values in the formula for 3 different penetration materials. For this buck converter, you can see the comparison between 0.13 mm in the black line, manganese zinc in red, so what is nickel zinc in green? The following diagram shows the current distribution in a conductor, in this case, 25 degrees Celsius. As this frequency increases, the skin depth decreases, iron powder and the cross-sectional area as pure inductance as well, up approximately 400 kilo in resistance. The loss component, you can calculate this cross-sectional area up by multiplying 10 mega times pi times the radius core would times be ineffective in the frequency range above the diagram shows 3 examples of this scheme. Now, manganese, as you can see, are inductive up to frequencies around 20 and 38 millimeters skin depth. Losses are usually rising above 10 megahertz frequency to and 10 the core material is no longer would be less in the frequency range above 80 millimeters. And finally, if we increase to 400 kilohertz up to frequency of the skin around would be even smaller. 0.1 millimeter. Keep increasing this value, the core material is no longer effective. The area above approximately 1 gigahertz is going to be limited by this value. This is something very important to take into consideration demonstrates when handling high frequency are predominant in the EMC field. The core material can perform an effective filter function within the frequency range of the greatest interest. Let's talk a little bit more about the rated current. We can also point out the typical initial permeability current of this core as the current that causes the inductor to heat up above ambient temperature cores have a permeability between 50 and 150. This is different from saturation current and may be a larger between 300 and for example 20,000. If an inductor is operating at its rated current would be between 40 and 50 above the ambient temperature by the temperature stated in the datasheet. With that said, let's analyze how the permeability behaves temperature when the core experiences 40 degrees temperature change. However, the following graph magnetic initial permeability is not a function of temperature, And not all manufacturers use the same testing parameters. Was made at a frequency of 10 kHz. This is always something you must take into consideration of each core when comparing inductors between different competitors. Now, coils having the diagram on the right shows our measurement setup variable inductive to determine the change in the ambient temperature. We place there are two important concepts to take into consideration and power it with, of course, on one hand, the maximum operating temperature range, temperature sensor device, and on the other hand, the ambient temperature and the inductor's temperature. It is highly recommended all this information that the temperature of the component does not exceed this maximum operating temperature under worst-case conditions. This range is dependent on core material chemical formula. Let's discuss the self-resonant frequency. Well, the current temperature, every inductor has a very material coupling loses arising from its winding turns, and this is why the inductance drops to zero. This parasitic capacitances are symbolized on the graph by a capacitor C. However, equivalent circuit this condition is not on the top right diagram. Once the ferrite cools down, this capacitance in the coil forms a parallel resonant circuit. Generally, the higher the initial permeability, the self-resonant frequency, or SRF, and typically is the permeability presents a peak parasitic capacitance right before the ferrite reaches its current temperature, resonate with the ideal inductance of the inductor. The input energy oscillates back and forth between the elements of inductance and capacitance. The inductor only functions of the self-resonant frequency. If the inductor is operated above its resonance, the capacitance dominates, and in fact, the inductor acts as a capacitor. This is why they should always be operated below their resonant frequency. Also, at the self-resonant frequency, the impedance becomes very high, and the inductor can be used as a EMC filter choke. Take in mind that the higher the number of turns around a core will result in a higher inner winding capacitance. Therefore, this shifts the self-resonant frequency into the lower frequency spectrum.
This podcast was taken from a Worth Electronic webinar. To view the materials and replay the webinar on demand, simply click the link attached in this podcast. Now, as mentioned before, our presenter, Max, is a technical chat navigator at Worth Electronic Online. You can chat directly with Max and the team by clicking the chat icon at www.we-online.com. You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists. We're going to shine a light on topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast.